everybody, today we're going to start applying all of our stoichiometric conversion knowledge to actual chemical equations. Let's get started. Our first goal for this lecture is to be able to determine the number of moles of a product produced by a given amount of reactants. We'll then look at the law of conservation of mass and practice applying it to balanced chemical equations. And finally, we'll make sure we understand how to convert from any unit of measurement to any other unit of measurement. These types of conversions are going to be interwoven to problems throughout the rest of this unit, so I'd strongly recommend having your conversions reference sheet handy. Let's start by going over some of the basics of a chemical reaction again. Here we have a decomposition reaction of hydrogen peroxide going to water and oxygen gas. The coefficients tell us that for every 2 molecules of H2O2, we will end up with 2 molecules of water and 1 molecule of diatomic oxygen. And, since you're all expert on moles by now, we know that the same relationship applies to moles of each compound. For every 2 moles of H2O2, we will end up with 2 moles of water and 1 mole of oxygen. To check your understanding, we'll try some practice problems with different mole amounts, starting with this one. If we have 4 moles of H2O2, how many moles of water and oxygen will we end up with? Hopefully you came up with 4 moles of water and 2 moles of oxygen gas. Let's look at some more examples. The first reaction we'll look at is a combustion reaction involving C3H8. Using the balanced chemical equation shown at the top, try to answer the following question. If we start with 2 moles of C3H8, how many moles of oxygen gas will be consumed, and how many moles of water and CO2 will we end up with? Because we doubled the amount of C3H8 from 1 mole to 2, we would need to double everything else as well. This would leave us with 10 moles of oxygen consumed, 6 moles of CO2 produced, and 8 moles of water produced. Now, the second example is a little bit trickier. We start with 3 moles of magnesium. How many moles of oxygen are consumed and how many moles of magnesium oxide are produced? Pause the video if you need extra time. Our moles of magnesium go from 2 to 3, which is multiplied by 1.5. If we do the same to our other compounds, we get 1.5 moles of oxygen consumed and 3 moles of magnesium oxide produced. We already learned how to convert from moles to grams of a substance, so now we can use this information and the law of conservation of mass to predict the mass of products from a given reaction. Hopefully you'll remember from near the beginning of the year that we said that the law of conservation of mass says that mass cannot be created or destroyed during a chemical reaction. Let's say we react 3 moles of CuCl2 and 3 moles of Al. Without even knowing the products, we can predict their total mass. 3 moles of CuCl2 has a mass of 3 times 63.55 plus 2 times 35.45, or a total of 403.35 grams. 3 moles of aluminum has a mass of 3 times 27, or about 81 grams. Total, our reactants have a mass of 484.35 grams. If you can't do these calculations on your own, it's probably worth your time to go back over molar mass and mass to mole calculations. Now, due to the law of conservation of mass, we know that our products must have the same mass as our reactants, so the mass of the products must be 484.35 grams. Let's look at a few more examples. The first problem asks, if you react 14 grams of nitrogen gas with 3 grams of hydrogen gas to form ammonia, what will be the mass of your product? Now, there are 2 ways to do this, and we're going to start with the longer one on this first example. So first, we can calculate the molar mass of each of our different components. So the molar mass of each nitrogen molecule is 14, and each hydrogen molecule is 1. We have N2, so the molar mass of N2 is 28 grams. The molar mass of H2 is going to be 2 grams. And the molar mass of NH3 is going to be 17 grams. Now, in this case, we have 14 total grams of nitrogen gas, which is 1/2 of the molar mass, which means we have half a mole of nitrogen. And we could end up doing that entire equation out fully, but I'm not going to have space. With hydrogen, our total, we're going to have 3 grams, and since we have 3 over 2, we have 1.5 moles of hydrogen. And then with NH3, we have to figure that one out. But we can use this balanced chemical equation to determine that we're going to end up with 1 mole of NH3. Now, this is because we divided this one by half, or by 2. This one's been divided by 2, so we have to divide this one by 2 as well. We'll get 1 mole over here. Now, 1 mole of NH3, we determined that the molar mass was 17. If we have 1 mole times 17 grams per 1 mole. These will cancel out, and we're left with 17 grams of ammonia, which is actually the correct answer. The second one, we're going to do the faster way. This says if you burn 32 grams of methane gas, consuming 128 grams of oxygen gas, what mass of water and CO2 is produced? Now, you could go through and actually calculate the molar mass of each of these different components and do the whole thing all as a big process, but it's going to be a little bit easier to just do this. Our reactants have 32 grams of one plus 128 grams of the other, which is a total of 160 grams. And due to conservation of mass, we know that our products are going to have the same mass as our reactants, which is 160. So we just get the answer of 160 grams. Now, we can use the total mass of the reactants to easily predict the total mass of the products of a reaction, but with a bit more work, we should be able to predict the mass of all components of a reaction if we're given just one. This is a longer process, but it starts the same way as most stoichiometric problems do, by converting everything to moles. I can't stress this enough. If you're doing a stoichiometry problem, you'll almost always benefit from converting everything to moles. From moles, we should be able to convert back to whatever unit we need, as long as we use the balanced chemical equation. Let's look at this process in more detail with an example. So this problem says that we have 72.9 grams of HCl, or hydrochloric acid, and we react it with NaOH, which is sodium hydroxide, to form water and salt. What mass of sodium hydroxide should we use, and what mass of our products will we have? The first thing we need to do is figure out the molar mass of HCl. And we have hydrogen with a molar mass of 1, and chlorine has a molar mass of 35.45. We add those together, and we get the molar mass of HCl is 36.45 grams per mole. Now we have 72.9 grams of HCl, and we want to figure out how many moles of that we have. So in 1 mole, we have 36.45 grams. If we divide these out, we're going to end up getting that we have 2 moles of HCl. Now, the problem with this is that we don't have our balanced chemical equation written out. So we're going to go ahead and put that up here. It's going to be HCl plus NaOH, which goes to NaCl plus H2O. And that's actually balanced already. We've got one atom of sodium, one chlorine, 2 H's on this side, 2 H's on this side, and 1 O on each side. So this is all 1 to 1 to 1, which means we're going to need 2 moles of everything else. So 2 moles of NaOH, 2 moles of NaCl, and 2 moles of H2O. Now, in order to convert these back into masses, we're going to need to use the molar mass of each one individually. So, we know that the molar mass of oxygen is 16, and the molar mass of sodium is about 23. I'm going to go ahead and round because I don't really want to put in the time to figure out the full thing. So, NaOH, we need Na, which is 23, plus O, which is 16, plus H, which is 1. That gives us a total of 40 grams per mole for NaOH. NaCl is going to be 23 plus chlorine's 35.45, which is about 58.45 grams per mole. And then H2O, we can do the math for it, but it's just 18. And that's one that I've worked with often enough that you can memorize. So now we have to multiply each of these by 2. So with NaOH, we have 2 moles times 40 grams per 1 mole. We have 80 grams of NaOH. For NaCl, we have 2 moles times our 58.45 grams per mole, which is going to give us 116.9 grams NaCl. And lastly, we've got 2 moles of H2O times 18 grams per mole. And that's going to give us a total of 36 grams of H2O. We can combine this technique with other types of conversions to get to any unit that we want. This is important as it is unlikely you'll be measuring all of your substances in grams in a lab. The states of matter here will also become important, mostly to distinguish between volumes of liquid and volumes of a gas, which require different conversion factors. Let's try an example. Alright, so this example problem tells us that we have 5 molar HCl and 2 molar NaOH. Now remember that molarity is expressed in moles per liter. We use 100 milliliters of the HCl solution. How much NaOH should we use? Now, this is the same reaction that we did before. So we've got HCl plus NaOH goes to NaCl plus H2O. So in this case, we want to use a 1-to-1 ratio. If we're using 100 milliliters, we need to convert that to liters. So 100 milliliters times 1 liter per 1,000 milliliters equals 0.1 liters. And then we've got 5 moles per liter. Gives us 0.5 moles of HCl. This asks us how much of the NaOH solution should we use. So we need 0.5 moles of NaOH since they're reacting in a 1-to-1 ratio. And in this case, we know that we have a ratio of 1 liter per 2 moles. So these will cancel out and we'll get 0.25 liters or 250 milliliters. Now this next one asks what mass of NaCl is formed. So we can start by just using these moles again. We don't have to reconvert from the beginning. So we have 0.5 moles, and that's going to end up being the same for NaCl because our reaction is a 1-to-1 ratio. So we have 0.5 moles of NaCl, and we want to get 2 grams of NaCl. The way to do this is using the molar mass, which we calculated earlier to be 58.45 grams per mole. So half of 58.45, we get about 29.2, and I'm just going to round. So we get 29.2 grams of sodium chloride. Last one asks what volume of H2O is formed. Now, normally, if we were doing a volume of a liquid, I would have to give you the density, but the density of water is 1 gram per milliliter, so that makes everything pretty easy. We need 0.5 moles of H2O, and since we're using the density to eventually get to volume, that means we're going to need a mass first. Molar mass of water is 18 grams per mole, so we're left with 9 grams of H2O, and for every gram we have 1 milliliter, so times 1 milliliter per 1 gram, which gives us a total of 9 milliliters of H2O. Let's take a minute to try and summarize all of that math. Using balanced chemical equations, we can predict the number of moles of each reactant and product in a given reaction. We can use the conservation of mass to predict the mass of products produced in a given reaction, given the mass of the reactants, or vice versa. Using molar mass in the balanced chemical equation, we can calculate the mass of every individual reactant and product in a chemical reaction, assuming we are given at least one. And lastly, with our various stoichiometric conversions, we can determine the amount of any product or reactant used or produced in a chemical reaction if given at least one. And we can do so in the units that best apply to each component. Now, this lecture covered a lot of material, so don't worry if things are confusing at first. It'll take some practice to get all of this stuff down, so stick with it and don't be afraid to ask for help. That's it for today's video. I'll see you next time.